Ну, через секунду. Пошло? Ага, отлично. Да, no, on previous class we have started discussing closed principal ideal theorem, and also we have, I realized that we haven't discussed Nakayama lemma, which is one of the main tools. So actually, in Matsumura book on commutative algebra, Nakayama lemma is denoted like Nakayama and referred to Nakayama himself. Akizuki and Krul. So, of course, generally we refer this to Nakayama, but it seems that it was well known for many mathematicians at that time. Many of them realized that it is important too. So, what does it say? Suppose A, so we start with A and M is a local ring. So meaning that M is only maximal ideal. Of course, it is very easy to reduce to this situation since we can localize. Yes, so just we can reduce to this situation. By considering AP, yes, it's for P prime. And it says the following: suppose that M is a finitely generated module. This is very important, being finitely generated. Over A, and assume that M is equal to M times M. Yeah, so then M is just 0. So let us, this can be derived by several methods. Also, there is a generalization. Yes, only I should refer this everything to proposition, but it is called so first is called the classical Nakayama lemma. So generalization is the following. So we consider J to be the so-called Jacobson radical, so which is the intersection of all maximal ideals in the ring. In A commutative ring, M is finitely generated module. Then you just say that if Jm is equal to m, then it follows that m is equal to 0. Yeah? So let us derive this, and actually we had a lemma that do it almost instantly. You have to notice the following, that if you have an element, if x belongs to j, then 1 plus x is invertible. Actually, we had the characterization that, yes, so this, we had the characterization of G on the first lecture. Of J that x belongs to J if and only if 1 plus xy is invertible for any y. Yeah, this is just to recall. Yes, so this won't be used in the proof. But notice that we had the following lemma, that if you have a phi to be endomorphism, so lemma that we have proved, and we used it for integer elements, that if phi belongs to the endomorphism of m over a, meaning that this is the map that commutes with multiplication by a, then and m, if phi of m is equal to I times m. Yeah, so you apply homomorphism, and it is equal to I times m, meaning that we can write it in terms of any element here. Yeah, so that the element phi of m is written in terms of ai, mi, where ai are from I and mi are from m. Yeah, so then there exists a polynomial, so tn plus an minus 1 integer polynomial, which was actually the characteristic polynomial of this endomorphism written in a special way. Yeah, so then such that it simply annihilates, yeah, so this endomorphism. So just 2, etc. plus E0 is equal to 0 in endomorphisms. So this means that you have, so we can apply this, so given, so proof of the lemma that, so we do not recall the proof of this lemma that gives you integer polynomial, but given equality m is equal to I times m, we can view it as the composition of unit, yes, so that you can think that 1 times m is equal to I times m, or sits in, yeah, so sorry, here there is not equality, so in general it can be not equality, but inclusion, and of course, here, of course, yeah, so here it is inclusion, but of course, since m is larger, then I am. Yeah, so here you have equality, and so put phi equal to 1, and if you apply this to operator multiplication by 1, you get a polynomial that annihilates any element of m. So this means that for any m, inside m you have the equality, so 1 in the power n plus a n minus 1, 1 in the power n minus 1, etc. plus a0 times m sits inside the I times m. Oh, sorry, is equal to 0. So this, of course, for us, it gives you the following. So this is just unit, and the remaining part belongs to J. Yeah, so here I forgot that we had ideal J. Yeah? That was radical, Jefferson radical. So it sits in J. So this means that it is an element 1 plus x times m equal to 0 for x in J. And this means that m is equal to 0 since 1 plus x is invertible. Yeah? So since we can multiply by 1 plus x inverse. So this proves this part of Nakayama lemma, and of course for a local ring, Jacobson radical coincide with the maximal ideal, so you have automatic consequence the initial Nakayama lemma. And there are some generalizations. Yeah, so generalization. Important generalization that we can write down the following, that you take m, suppose you multiply, suppose you have modulo A is a local ring. So you have n inside them as submodule. And so such that so if you take larger module and multiply by m, so meaning that the larger module can be written as the larger module multiplied by m plus remaining part. Yes, so the right hand side, in principle, it could be smaller than n. So if you have this equality, then you have m is equal to n. Yes, m is equal to n. So this tells you that you cannot generate the module by the elements divisible by m, by elements from m, and the smaller, properly smaller submodule. And the proof is easy. Yeah, you just take the image of this thing inside m modulo n, and the left hand side is just m modulo n, and the right hand side is just the following. So if you take modulo n, this adding n does nothing, and if you factorize it, then you can write this down, that this is m. So this sits inside this sits inside m times m modulo m. So by Nakayama lemma, Yeah, so of course these are finitely generated modules. Or even more generally, they should be finitely generated modules for the quotient. Yes, so not all of them, or a weaker condition that m modulo n is finitely generated. By Nakayama lemma, we have m n is equal to 0, so m is equal to n. So this tells you, so let us derive something interesting from the beginning. Yeah, so just consequence. For example, you can do the following. So this is some kind of reason of introducing the p-adic topology that we shall maybe discuss later. But this is so for local ring. So this is local ring. So then. This is called the Krull intersection theorem. So if you intersect all of maximal ideals, the powers of maximal ideals, you will get 0. And the proof is very easy. Yeah, so this is a new theorem. So the proof is easy since we can put m equal to this intersection, and if you multiply m by m, yeah, so what you get? Yeah, so you get that you multiply intersection by, yeah, so n is bigger or equal than 0, and if you multiply, yeah, so you get the intersection of n, where n is bigger or equal than 1. And of course, this is the same, so this is the same of initial than that initial n, because you have inclusion of the powers of maximal ideals. So since we have m sits inside m squared, m squared sits in m, etc. Yeah, so that your intersection with m does nothing for this intersection. And by Nakayama lemma, yeah, so you this is ideal in the ring. Yeah, so it is a subset of the ring. So this is ideal. So m is finitely generated. So since A is Noetherian, m is finitely generated as ideal. So ideal. And the module.
So what is m to the power 0? What is m to the power 0?
What?
M to the power 0. When n is equal to 1, then what will be the power of m?
Yeah, so that you are right on that to say that. Yeah, so this, I mean, usually the 0 power is, usually one denotes m0 to be the whole ring, but I mean for some grading reasons, but of course this operation doesn't make sense until it is just defined by this formula. So I just, you're right that it is better to write this down like this. Yes, but this is bigger than 1 and this is bigger than 2. So, since M is finitely generated module, it is finitely generated ideal, and then it is finitely generated module. So this implies that M is equal to 0 by Nikayama by first property. Also, it is important to notice that so we have discussed the following. So if you take, so this is the basis of modules over local rings. So basis, well, this is not the basis, but the set of generators. So this is generators of the modules over the local rings. Yeah, so this is important observation that is used very frequently in algebraic geometry and of course in commutative algebra, that you have the following. So you can take M, so the module, and you can tensor it by so a module. So this is local ring. So you can tensor M by a modular M, and this is just a vector space. Yeah, so this is a field. So since this is a field, so the remaining thing is a vector space. So this is vector space over A mod M. And you can pick up bases here. Yes, so just M1, etc. M key, M as a basis. And also, you may think of this guy as just so you can prove directly or just by considering the following. So you just you can consider the vector space that looks like this: M modular MM is actually isomorphic to this tensor product. Yeah, so you have this, you can notice that this is also a module over A modular M, just by multiplying by the representatives, and you have, you can map actually this thing to this quotient. So in this direction, yeah, and this will be isomorphic. Yeah, so you have a multiplication map, and this will be isomorphic. So now, or you can think of this as considering exact sequence, like this exact sequence. And if you multiply it tensor just in a tensor way by M over A, yeah, so then this sequence won't be exact as the whole sequence. I mean, if you just rewrite it, but if you drop the left 0, it will become exact, which is just not very complicated to prove. So this is more or less evident. And here you have M tensor A modulo M. This is surjective map. And the one can notice that the image of this map, what is this image, is just mapping. So your image here is a submodule. So you just map the element from here and multiply. Yeah? And, so this is just that we denote by m times m. Yeah? So that you see that this part is just a quotient by this module modular the image, and this is precisely exactness. So I mean you can write this down in general by considering so exact sequence of n1 and 2 and n3, and by noticing that this will be exact if you drop those. So you have anyway, you have this isomorphism, and you may lift this basis to m. Yeah, so lift basis to m. And so I claim that this will be the set of generators. So M1, Mn, so then M1, Mn is the set of generators of M. And this is a very general observation. It is used everywhere, so let us derive it. Proof. Yeah, so just otherwise you may put n equal to m1 mn, and what does it mean for us? So if you take these generators and reduce it. So if you take it modular m of m, so it will generate. So this will generate by definition. So this, since the reduction is the basis, so the reductions will generate the whole m modular mn. And this means that, of course, that m. So if you take the module generated by them, so a modular mm, it is the whole module. So if you add elements of the form m times m, you get the whole module. So this is just Nakayama lemma. So this is Nakayama lemma. So this implies that so that n is equal to m. So this means that these elements generate the whole module. It is the
I didn't understand how you, I mean.
This.
Yes.
Yeah. Yeah. You see, I mean, if you take n. And reduce it, look the map here.
Okay.
Yeah, so that means you will get these elements, this collection of elements.
Yeah.
That is assumed to be the basis.
Basis of m.
Basis of m modulo m.
Mm-hmm.
And so I write down this equality.
Okay.
But if I write down this equality,
Mm-hmm.
this means that if I take representatives, so any element of m, modular, if I add n element of m, can be written in terms of linear combinations of this element.
Yes.
So this means that if I look at the lift, that any element of m here, yeah, so can be written modular these elements as the linear combinations of m's before the reduction. I mean the following. So this means that just the reductions I mean that if you take any m, so maybe I should write it more a little bit longer. So let me just write it down. That if you have m that is written, so any m, so any m in m. Yeah, so you can look at reduction, so you can reduce it modulo m, and this means that m can be written as a I mi over line modulo and m m. But this when you lift, yeah, so then this means that you can consider the following. So this means that actually the difference m minus. So you can consider the following difference m minus a I m I, just these guys, and this will be equal if you reduce it modulo m. So this will be equal to m minus a I until the I modulo mm, and this is just zero by the assumption.
Yes. Okay.
So we have just chosen this decomposition because of the basis here. So this is a basis.
Yes.
So you just play the game that you write down the element a priori. You know what it is, and
Okay.
and this means that n is equal to m, and this actually means that if you have the collection of generators, then I mean that generates the corresponding basis of the reduction, so that it is the set of generators. Of course, this doesn't mean that they are. This is somehow the substitute for linear independence. Yes, so because as we noticed, as we know that for abelian groups, for example, Z mod 5Z, we do not have Z mod MZ. Yes, so you do not have basis when you do not consider it over. So when you consider it over Z, so this is Z modulo 5Z. Yes, so over Z doesn't have a basis. Yes, so over Z does not have a basis. Because unit is annihilated if you take 5 times unit. Yeah? But in a sense, when you consider this as over Z modulo 5Z over Z modulo 5Z, there is of course there is a basis generated by unit elements. So since this thing is a field, and you can think of this as, I mean, this is not a local ring, but I mean that, so here you have the situation that is Z mod 5Z is generated by one element. So the similar, I would say the similar situation. So this, yeah, so this is what about can be said about the modules. Yeah, moreover, yeah, so there was some remark that notice that so importance of new radical of H. So if as the ideal, yeah, so if you think of this as so nil radical, of course. So if you consider it over the local ring or over so anyway, so nil radical is just equal to the intersection of all prime ideals, yeah? And this sits in so this sits in the small intersection of all maximal ideals, and so primes are. So it since all maximal are primes, and this is Jacobson radical, yes, so as we have discussed. So, or more just if you have an nilpotent element, it's trivial that 1 plus nilpotent element or 1 plus y times nilpotent element is invertible, so you can use the other definition if you like. But notice that you can consider the powers. Yes, so and suppose you have Artinian and plus Noetherian property, I mean simultaneously. Of course, we derived that Artinian implies Noetherian. But if you assume before them both, yes, Artinian plus Noetherian allows us to prove the fact that implies that nil radical of A in some power n is equal to 0. So since so you can consider decreasing sequence. And if you consider this decreasing sequence, yes, so Artinian property implies that it stabilizes. So you get that nilpotent A n is equal to nilpotent radical times n plus 1. And this is precisely if you put just put this equal to J. Yeah, so equal to M. Then this implies that M is equal to nil radical of A times M, and it sits inside J times M, where J is Jacobson radical, and this implies that M is equal to 0, since also you have we assumed additionally Noetherian. So here we have assumed the important property, the Noetherian property. So just by Noetherian property, M is finitely generated. So by Noetherian property, M is finitely generated. So by Nakayama lemma, M is equal to 0. So of course this is a bad proof because you cannot. So we have to assume you cannot apply Nakayama lemma directly, and you have to make assumption of Noetherian property. And if you remember, if you recall, we have derived the classification, more or less classification of Artinian rings, and a posteriori we have derived the Noetherian property by knowing that Jacobson that nil radical is nilpotent ideal, and this is of course a disadvantage of this proof, but yeah, I mean it is good to understand that this is just, I mean, one of the consequences of Nakayama lemma. Just for the general, I would say, intuition. So, okay. So this is what I wanted to say about Nakayama lemma. So let us pass to Krull principal ideal field. So, but before I would like to discuss the so-called symbolic powers. Yeah. So, what are they? So, why we should consider symbolic powers? So, let us state the following problem. I mean, it's not it is problem of the nature. I mean, it's not the problem to solve it. I mean, it is already solved. The problem is that if you have that 4 prime ideal, P. P to the power n in general, P to the power n is not primary ideal. So we shall have a sheet and example when it happens. And in order to tackle this problem, yes, so we have to notice that observation that if AM is so if you have M as maximal ideal, so M is a maximal ideal. And you have the property that yeah, so if you have the property that if Q sits, so it is ideal that sits in the maximal ideal, and and sits in M, so it sits between these 2 ideals, then Q is primary ideal. And actually it is associated with this maximal ideal. And why it is true, so you can consider A mod Q and consider annihilator of N mod Q. And you of course notice the following, that so since n is a subset, yes, so that unit in A mod Q is so the ring is annihilated by m modulo n, and in particular by all powers of the elements, and by all powers where m belongs to the maximal ideal. Yeah, so so this is just part of the condition. Yeah, but notice that this implies that radical of the annihilator. Yeah, so that if they are annihilated by these powers, so radical of annihilator contains all it contains all the maximal ideal M. But notice that radical is intersection of all prime ideals, where prime ideals belong to the set of associate prime ideals. Yes, so actually we had the formula that says that this is the set over intersection of prime ideals over the support of M. And since when you are intersecting the elements, you can consider only minimal elements in the chain. So you also put minimal elements of the support. Yeah, so you can write this down, that this is intersection of E belongs to the support, and P is minimal. Yeah, because it will be just out of the chain. Yeah, so you can keep only the minimal element. Yeah, so when you consider intersection, and this is also equal to the set of intersection of all minimal elements. So this tells you, and M is maximal ideal. So since M is this means that yeah, so it contains the maximal ideal, and this means that maximal ideal is contained in this intersection of prime ideals. Yeah? And you have to use the following. I claim that out of this I can derive that the set of associated devices is just M. Yeah, so how do we how we can make it? So use lemma. So again, let us recall lemma. That if you have P prime ideal, and P sits into in the intersection so this here you have actually so here the inclusion, so m sits in this intersection, but m is maximal, so just we have to derive out of this that this intersection is actually the same. So since m is maximal. And of course, this implies that if it's so this means that m sits in any p. Yeah. So actually, I wouldn't just I mean just I should have written just I mean this lemma can be used, but not in this simple situation. It can be used in more general, so refer to this case. Yes, so this implies that m sits in any p. So for any p inside the set of associated prime ideals, and this is minimal. Yeah, so and actually you even do not need to assume that the minimality. So this implies that m is equal to p. So I mean, just you can let me put it in the brackets that we just do not use it here. I mean, so don't use it. Okay? So and you may use only use this one, and this implies. Or actually even the support, and this implies that the set of associated prime divisors, so this implies that the set is equal to only ideal m, so the ideal is prime. So Q is primary module, submodule of A. So it is primary ideal. So anyway, so what is used here? That the radical is maximal ideal. So as soon as the radical, so more generally, suppose. So more generally, so if you have n primary submodule, so n is submodule, such that annihilator of m modulo n contains m and for maximal ideal. So this implies that m is primary associated with m. So this this is the first observation that what happens, and geometrically it is just so you are thinking as the module or decomposing ideal in the components, and as soon as you see that the set is associated. So, meaning that annihilator contains the power of maximal ideal means that you have geometrical means you have only one component that corresponds to this maximal ideal, and this is precisely so the module is decomposed as just as I would say it can be filtrated by the ideals of the form A module N. Yeah, so by the modules, so that you have a sequence of modules so that can is isomorphic to A module N. So now this yeah, so this is what I wanted to say about the maximal ideals, but then let us return to symbolic powers. Yeah, so that Pn is not primary, but you can ask what is the support of it and what is the set of associated prime ideals. So the claim is that, but P is minimal. Yes, so let me write it down as a proposition. P is a minimal component of the set of associated primes A modulo P to the power n. So it is it is not primary ideal. It doesn't this set doesn't consist of P, but this is the only minimal component. Actually, this is the only minimal component. All components are contained inside, so that they contain. So all other prime ideals that are in the set of associated prime ideals that they contain P. So the proof is easier, as we have noticed that yeah, again, annihilator of A mod Pn, it contains P to the power n, and this implies that just P in the power n annihilate belong to annihilator of A mod P n for any P inside P, and this implies that as before, that P sits inside radical of annihilator of A mod P n, and so notice that yeah, so radical is just the intersection of P, where P is minimal, P tilde, yes, minimal in the set of associated prime ideals. Yeah, and one see the following, yes, so that this it tells you that a priori, if yeah, so Yeah, and yeah, and also notice that just also yeah. So here you should be a little bit more subtle. That just that P P set. Yeah, so this, yeah, so actually out of this, you derive, yeah, I mean, you can even not use this formula, but this of course implies that P is a subset of P of n for any P tilde in the set of associated prime devices. Yeah? And on the just a second. And then you can, now we have to prove that P is actually essential. I mean, you can find such component, and this can be proved as follows. So we can do the following. So that let us recall that what we know from associated prime decomposition. So we know that that e to the power n is equal to q1. So you are writing down it as intersection of some primary ideals, qi are primary ideals. And if you want to derive the primary component, the minimal primary component, so if you have qi primary component ideal associated to ei, which is minimal, in the set of associated primes, then we can reconstruct qi by the following. Is equal to if you take the map which is localization by pi, yeah, so this is just a localization in the ring. And then qi can be written as mapping, so you are mapping it pi, so you are mapping the initial ideal to the localization and take its preimage. But notice, and what can be said that, so what we have proved when we addressed the primary decomposition even if anyway, so if you take any module and localize and put it back this way, that you will get the primary submodule. Yeah, so this this is primary, and if you notice that so if you notice that when you localize, so P becomes is maximal in after localization in AP. Yeah? So this implies that by previous step, p to the power n, yeah, the power of so in particular we have considered the ideals that contains the power, so we can apply to p to the power n is primary in a mod p associated to p, and we can recall what happens when you consider localization. Yeah, so if you take M and you take localization with respect to multiplicative set, so this was just intersection of the set of associated prime ideals and the preimage. I mean, if you take this I star, the inclusion of spectrum of localization to the spectrum of we are putting that we are considering the subset here P is such that P intersection with S is empty. Yeah? So this is just the intersection of I star of spectrum of AS, and this yeah. So since yeah, so all ideals by previous assumption, so by previous observation. If you look at all P tilde, so P tilde, so that belongs to the set of associated prime ideals, they contain P tilde contain P. Yeah? And this implies that P tilde has a non-zero intersection with S for S is equal to the complement of P. Yeah? So this means that just all ideals die except this P tilde, which is precisely so since you know that since P is inside the set of associated prime devices, I mean here you just yeah, so this implies that P is contained in the set of associated prime devices. So I just wanted to say that you can derive it that the preimage of this ideal is associated prime, but you actually do not need this. You see that since you know that this set is, after you localize this set as P, you know that, I mean, this is not needed, so this was just observation. Don't use. Sorry. Okay. I mean, we just use that this is not the localization, so put it here. So maybe let us stop and let us so far what is the definition of the symbolic powers? You can write down explicitly what does it mean for us, and for us this means that just you can define this symbolic powers more or less explicitly by the following formula. So this is just the set of P inside A, so such that so there exists some S that belongs to the multiplicative set, the complement of P. Yes, so such that SE belongs to P to the power n. So this is precisely checking that something belongs to localization. Yes, so that we recall that. Yes, so that your if you want to compare elements and just they belong to the image in the localization, that it means that you are allowed to multiply by invertible elements, which is precisely this thing. And if you want to check that P, that element P of the form E divided by 1 belongs to the image of IP, IS of the localization, where you are considering more general the localization of this form, so F, AS, IS. Yes, so it belongs to the set IS of some subset N. Yes, so N, for example, was a subset in A. Yes, so this implies that you have the elements can be written in the form, so P divided by 1 can be written of the form N divided by S, and this is in ES. This implies that P times S. So this doesn't. So notice that here we have to have some multiplicative properties. So maybe I should write down ideal. Yeah. So maybe. So let me put it as some modules. So if you have M, the localization in the module M, if you have M that you want to write down as N as a module, so this means that M divided by 1 can be written as N divided by S in the localization, and this means that up to that there exists T such that MS minus N T just a second. is equal to 0, so that means that m is equal to n and ts. Yeah. So okay. So let me do the break.
I didn't understand the last calculation. How m becomes n?
Yeah, so this is just I didn't want to say this. So just yeah, so this means that ms. Yeah, so it means this one.
Yeah.
And this implies that ms is equal to mst, yeah, so is equal to nt. If you put this to be ms tilde is equal to nt, so this is an element of n.
Yes.
So this is precisely meaning that the n times s tilde belongs to
okay.
this, which is written.
Okay, okay.
Yeah, sorry, I was
Tilde.
in a hurry.
Окей. Нет, я понимаю, да.
Там
Но я просто на слух, типа, задаю ноты, не очень могу полностью воспроизвести.
ну да, там есть такие художественные места, в принципе.
То есть, что ты вообще делаешь? Какое ключевое построение?
Ну, я беру, раскрываю 6 точек.
Каких?
Это положение.
Сейчас, лежащих внутри кубики или что?
Нет,
Как это?
на плоскости есть 6 точек, я их раздуваю, получается кубик.
Погоди, реально получается кубик?
Да.
Кубической.
Ну, кубическая поверхность.
Ну, да.
Да, но это вы делаете просто таким образом, что у вас есть линейная система, вы должны сделать две вещи. Первое, ну, в смысле, что вы должны определиться, как вы, как вы вашу поверхность с раздутыми точками вкладываете. Это получается по как бы линейной системе. То есть вы должны взять канонический класс, ну, антиканонический класс на этой поверхности. И он как бы равен минусу от тройки, ну, то есть канонический класс на плоскости, и минус вот эти вот исключительные кривые вот в этих раздутых 6 точек. Вот. После этого, как бы, вот, когда класс взят, нужно что сделать? Нужно применить теорему Римана-Роха, да, чтобы получить размерность, ну, вот этой линейной системы. И, ну, как бы вы получаете, что она 4, но это вычисление, плюс нужно две вещи. Сама теорема Римана-Роха, да, которая считает размерность, плюс теорема об обращении в ноль, которая гарантирует вам, что вторые и первые homологии равны нулю. У вас только ошибка считается, потому что теорема Римана-Роха — это Эйлерова характеристика равна вот этому индексу значения. Вот. После этого вы как бы получаете, что, ну, вы должны показать, что ваша линейная система также не имеет базисных точек. Вот. Ну, то есть, как бы, что у вас, вы можете взять пересечение, грубо говоря, двух, ну, эта линейная система, она порождена следующим, но вы просто должны написать уравнение кубической кривой, которая проходит через эти 6 точек. Таких кривых много, и, как бы, грубо говоря, на самом деле нужно сделать следующее, чтобы это понять, что у вас, как бы, ну, грубо говоря, через 9 точек вы можете провести кубическую кривую, да, каждая точка задает существенное условие. То есть, ну, например, что то есть вам нужно вот через эти 6 точек проводить такие кубические кривые, ну, как бы, чтобы показать, что нет базисных точек, нужно показать у линейной системы, то есть когда ваше сечение не обращается в ноль. Нужно просто показать следующее, что у вас вот эти элементы из линейной системы, вы можете найти два не пересекающихся элемента. Но они будут пересекаться по вот этим 6 точкам, но как бы ваши элементы из линейной системы, они пересекаются по 6 точкам все, ну, потому что это условие. Но вы должны показать, что они не пересекаются, можно найти такие элементы, которые не пересекаются снаружи этих 6 точек. Но это можно искать в виде вырожденных элементов, типа коник, ну, типа прямых, например, ну, как бы, или, ну, в смысле, но там, как бы, вот эти точки не лежат на прямых, ну, там 5 точек лежат на конике, поэтому можно проводить коники, да, через 6 точек, да, ну, прям через 5 провести конику, а через оставшуюся прямую, да. И вы показываете, что вот они не пересекаются, значит, вот эта линейная система выдает отображение проекте, ну, уже в проекте трехмерном проективном пространстве. А дальше вы должны понять, что это кубическая поверхность. Как мы выделяем кубическую поверхность? Мы знаем, что это поверхность, да, ну и теперь нужно только степень посчитать. А это просто вы берете гиперплоское сечение, да, первое, получаете кубическую, была поверхность, вы должны кубик получить. Значит, вы берете второе гиперплоское сечение, значит, вы должны 3 точки получить. Ну, тут как бы получается следующее, это значит, вот эта линейная система кубик, которая проходит через вот эти 6 точек, должны, значит, в оставшихся вот эти вот 3 точки, про которые мы говорим, это как раз ваши кубические кривые проходят через вот эти 6, но кубические кривые на плоскости, они же пересекаются по 9 точкам. Поэтому вот вам оставшиеся 3 точки пересечения, это и есть вот, когда вы отобразите вашу поверхность как поверхность, да, то вот они те 3 точки пересечения. А грубо говоря, вы делаете следующее, нужно написать, как бы вот по вот этим точкам, вам нужно просто написать 4 линейно независимые кубические уравнения, проходящие через эти точки. Это вот буквально написав вот эти 3 однородных многочленные, написав их, f от x, y, z, f1, f2, f3, и взять их как однородные координаты, дадут отображение вот этой штуки p4.
В P4.
В P3. Я оговорился, если тоже. 4 координаты. Давайте тогда дальше продолжим. Вот, so let us just discuss now cruel principal ideal theorem. And there we shall use symbolic powers. Principal ideal theorem. Suppose you have an element of A and P is associated prime divisor, prime ideal with the set of zeros A, so with so here it is geometric interpretation. So with modulo A, so so then P is of codimension 1. That means the following, so meaning that for any Q, that is contained in P, prime ideal, doesn't contain any Q does not contain any other prime ideal. Does not contain any other prime ideals. Yeah, so then this Yeah, so of course we are thinking about geometric interpretation that you are taking the zero set of A and you can consider the components of the zero set and that this they should be the set of dimension 1. So there was a tiny moment, so remark that refer to dimension. So if you think of crude dimension of the ring, then it is sequence of prime ideals. Yes, so P0, P1, etc. Pn. So this is Pi prime, and they are not equal. So and it is the maximal length of the chain. So maximal length of such chain of prime devices. More, if you want to consider so you can take ideal I inside the ring, and you may think of the corresponding notions for I. Yeah? But here, of course, you may think about ideals containing I, and you may think that about ideals that are contained in I. And yes, so notice that here I'm putting, it can happen that if A has 0 divisors, that 0 is not prime ideal. Yes, so that we are not putting 0 in the set of prime ideals. Instead, we are writing down P0. So also, if you have ideal in A, yes, so it is very easy to define dimension. So the so-called, so the thing that, so there is a notion of dimension of the quotient, which is actually the dimension of the zero set. Yeah, and also you may try to consider codimension, and naively. One wants to take ideals, yes, so it is as if you have a chain of prime ideals, yes, so if you expect that dimension plus codimension is equal to 1, it is as if you take a chain of prime ideal, you subdivide it into parts by putting ideal in between. The right hand side is the dimension of the zero set. The left hand side, the number of ideals that there is codimension. But notice that when you have this situation, it may happen that you raise the ideal in some large power, and if you raise the ideals in such power, this separation can move dramatically ideal to this side, and it won't be contained in some ideals that are sitting here. So the idea is to consider codimension is the chains that starts with minimal components of I. So you are considering minimal ideals, prime ideals that contain I. That contain I, and you start chains from these ideals. Yes, so you calculate the length of chains. Yeah, so this is a right definition that is have the geometric flavor, and it is really well given. So let us now pass to the proof. And you will see that that we have spent so much time on considering Cartesian local rings. It was not in vain for us. We shall see how to work with it. So notice that we are interested in ideals Q inside P. And of course, so since P is minimal over A, so this means that Q doesn't contain Q does not contain A. So otherwise, you can choose instead of P, you can choose Q. Also, we need the following remark. So when you are speaking about ideal, yeah, so you can consider, so there are two options. So you can, so we had the associate prime decomposition. So you had the minimal components of associate prime decomposition of associate primes of A modulo I, and you had minimal prime ideals that contain I, and so prime ideals that contain I. And actually, these sets are equal. So the claim is that these sets are equal. So let us notice this. And this is precisely the following. So you have, so you have the following picture that the first tells you that radical, that radical of associated prime ideals, of annihilator, yes, we can consider the radical of annihilator, which is precisely I, yeah? So radical of I. So this is a set of P, which is minimal. P is inside the set of associated prime ideals, and P is minimal. And so here this intersection is intersection, of course, contains I, yeah, so clearly. And just notice that if you have suppose you have just so you have so suppose that P is minimal ideal, minimal prime that contains I, yeah? what you may do with this intuition? You may take radicals. Yeah? So you can take radical of P, which is P. And this implies that it contains a radical of I. So this minimal prime ideal, so this means for us that this minimal prime ideal contains this intersection. And this implies that the following. So this we had the dilemma that I wanted to mention, that if you have a P prime ideal that contains such that P contains the intersection of ideals, then it contains some of them. Then P contains EI for some of them. And this implies that P tilde contains P where P belongs to the set of associated prime ideals, and this P, of course, it already contains I. And of course, since P tilde is assumed to be minimal, this implies that P tilde is actually equal to P, yeah, so to some prime component. So instead of thinking about, there are natural notions, yes, so the set of associated prime ideals that we used for decomposition, but here when we are speaking about ideals, we may use a weak and much easier notion for minimal ideals, yes, so minimal ideals that contain I, then minimal prime ideals that contain I are precisely the minimal elements in the set or in the support and the minimal set prime ideals that contain associated prime ideals. Yeah? So this so let us come to the proof of Krull theorem now. Yeah, so you are interested in the following situation. Q sits in P, and A is contained in P. Yeah? So notice that we will be also interested in saying that there are no ideals smaller than Q, so you can localize. Yeah, so when you want to speak about prime ideals that are inside Q, so without loss of generality, of generality, we can localize in P. And so we can assume that just AP is a local ring where P is maximum. P is maximum. So this after that we have the following picture. Yeah, so you can you want to so you have a ring here. You have ideal P. You have an element. Yeah, so you have. Yeah, so you have ideal P. It contains ideal Q, and here you have ideal A. And you want to start considering sequence that will move close to P. How you can do it? You can do it by adding to A some symbolic powers. So the idea now is to consider just AA plus QI, where you are taking this symbolic powers. Notice that we can take the symbolic powers only of prime ideals, yes, so because we have used the multiplicative set. Yes, so consider the sequence. Of symbolic powers. A plus QI. So notice that if you consider also take P and pass to the quotient of A mod A. Yeah? So A mod A. So what you get? This ideal contains so P contains A. Yeah, so you know, so this is of course a local ring. You have only maximal ideals. So just here P of P is only maximal ideal. So this is a local ring. And notice that you do not, so P is minimal, so P is minimal over A, is a minimal ideal over A. So this implies that there are no ideals no ideals in no prime ideals in P of P, and all ideals are contained in P of P. So P of P is the only prime ideal, no other. So P of P is the only prime ideal. And you may notice that red, so this implies that nil radical of A mod A is precisely this image of P. And this, nil radical, if it happens that nil radical is maximal ideal in a Noetherian ring, so A was Noetherian, A is Noetherian, where maximal ideal P is nilpotent, is nilpotent. So there was such lemma, and this implies by lemma in the sequence of So in the section of about Artinian ring by lemma, A mod P is Artinian, A mod A is Artinian. Okay, there was a lemma that if you have a maximal ideal that was nilpotent, then the ring was Artinian. This implies that the sequence just so the sequence Qi inside the A mod P, just images of these ideals. So it is decreasing sequence. So the powers form decreasing sequence. So this sequence stabilizes. So this implies just the images stabilizes, but so this implies that just P of Qi is just equal to P of Qi plus 1. I want to write it, what does it mean modulo A? So this implies that Qi plus A, yeah? So ideal generated by A. So this is a priori, Qi plus 1 is a priori smaller, yeah? So this is equal to Qi plus 1 plus A. And this implies that you can put, so the problem, so the equality implies that actually Qi is already contained in Qi plus 1 plus A. So what does it mean for us? So that X here that belongs to Qi can be written as Qi plus 1 is symbolic powers. So this can be written as Y, where this is an element of symbolic power, but you may think of this as the element, so we shall use that this is an element of Qi. This is also, we think of this as an element of Qi plus AB. So this is plus A times B. And this implies that A times B belongs to Qi, this Qi symbolic powers. But notice that here we can localize by Q. So we can localize by Q. Q. And here, of course, note that A was not in Q. Yeah? So after localization, so A was Q was the minimal element inside. So P was the minimal element over A. So if you take something smaller than P, it won't contain A. So this implies that simply that A is not in Q. So this implies that of course that B then B so in localization you will have this kind of thing, but this implies that if you recall the definition of symbolic power, you have to localize, and so B times A sits inside Qi after localization. And this since E is not inside Q, this implies that B should be in the symbolic powers by definition. So B belong in the symbolic powers. Note that the elements of the symbolic powers are such elements that if you multiply by some element, it will belong to Qi.
Yes.
Yeah, so that means that so here is there is small subtle moment because we check this in the localization, so that means that B, this is, they belong to the symbolic powers, so that maybe we should also multiply by some other. I mean, since we are here already in symbolic powers, maybe we have to multiply by some S that is not in Q. Yeah, so this is definition of symbolic power, and this means since this product is not in Q, then B is just in this Qi. But what does it mean for us? This means precisely so let us look back at this equality. So this means that B is now the element of Qi, so you can write down the equality x is equal to y plus AB in the following form, that x belongs to Qi, yeah? So y belongs to Qi plus 1, yeah? And again we refine, and here B also belongs to Qi. Yeah, so by this problem, yeah, so we have already proved. And from the viewpoint of inequalities, this means that, and this is true for any element of Qi. Yeah, so this is true for any element x in Qi. So that means that we have written Qi, which is the largest set, yeah, in the form of Qi plus 1 plus A times Qi. And the A is now in P. So now this is equality in equality in A P. So where you in the local ring corresponding to P. So and the A is belongs to P. Yeah. So recall that we had the form of Nakayama lemma. So that if you have M maximal ideal, and if you have M times M plus N equal to M, yeah, so then N is equal to M. Yeah? And here you have precisely this situation, that here you have, so this is M, this is M times M. Yeah? It is a subset of M times M, and Qi plus 1 plays role of M. So this implies that by Nakayama lemma applied to the local ring AP and maximal ideal P implies that Qi is equal to Qi plus 1. So we have derived the stabilization of symbolic powers. But then we can, when we see this equality, of course, symbolic powers we do not know how they behave, but you can look at localization. So pass to localization. And in the localization, it is just the equality of ordinary powers. So by Nakayama lemma, again, applied to AQ, this implies that Q is Qi is equal to 0. Yeah? And what does it mean now? So now we have to derive so what we have obtained that Qi is equal to 0 where in AQ, and this now this is a local ring. So Q is a maximal ideal. This implies that Q is a maximal nilpotent ideal. Ideal in the Artinian local ring. In the local ring. Local ring. And this implies that the ring is Artinian. But in Artinian ring, all ideals has all prime ideals are maximal. So just in this implies that all prime ideals are maximal. Maximal. So Q is only, this implies that Q is only a maximal and prime ideal, so it is only prime ideal. So this implies that there are no small ideals, there are no smaller prime ideals. That there are no prime ideals that are contained in Q. So just hopefully that are contained in Q. So that proves Grove theorem. So yes, this proof is rather tricky, but you should think that just in a sense this taking powers, yes, so this is somehow considering the infinitesimal neighborhood of your variety, and if you have, so what is said here that if you have non-trivial variety, so that of dimension more than one, then powers are just so you are taking powers, and they cannot stabilize. They are if you are in the case when they are stabilized, the localization of the ring is Artinian, and this is precisely the case with the. Yeah, so how we can, what are just generalizations of rule principle ideal theorems? So you may consider system of parameters. You may consider many elements and try to calculate the dimension of the ideal that you want to obtain. So let us discuss this kind of things. So system of parameters. Yeah. So consider the following so let us prove the following proposition, which is not completely evident. So suppose you have x1, x r is the system of parameters, set of elements, and P is a minimal prime ideal containing so the ideal generated by this system. Then, so the claim is that this is very natural geometric claim, but it's not so natural in the sense of commutative algebra. Then P. Then you can calculate codimension of P, and codimension is smaller than the set of equations that are used to define this P. Yeah. So of course, if you have right notion of codimension, so then I mean, if you already have notion of dimension, and you can calculate the codimension by saying that you just add an element and you have to subtract one from the dimension. Of course, this is evident, but this is not entirely evident in a sense that you have to take the sequence. So this is so here just in algebraic geometry you have the property that dimension plus codimension is equal to dimension of the ring, and here this it is so here it's much more subtle in commutative algebra, because, for example, in algebraic geometry, you prove the idea is to prove that the notion, the crude dimension that we considered here, can be rephrased as the following. It is just transcendent. So we had the Noether normalization theorem, yeah, and one proves actually by using Noether normalization that dimension for the commutative algebra is finitely generated over the field is equal to transcendence degree of the corresponding fraction field over the field you are considering. And then this, if you have two sequences of, in particular, as a byproduct of this proof, that if you have two different sequences where you cannot put of sequences of varieties, yes, of reducible varieties, where you cannot enlarge the chain by adding new subvarieties in between, so a posteriori, it says that all length of the chains are equal. And in algebraic geometry, this is not the case. So there are chains that are maximal in the sense that you cannot add something, but they do have different length. So the reason is then such rings that behave this in a good way, so that all chains between any two prime ideals has the same length are called universally catenary rings, and this is a class of the rings. So this is not
Это по-русски.
универсально-катенарная просто.
Окей.
So this is called catenary. Yeah. And this, so that's why such theorems about, that's why the Krull theorem is formulated in terms of co-dimension and in such non-evident way that you can, that you expect. It is not like saying, so otherwise, if it was evident case, yes, so otherwise I would simply say that dimension of P is just the dimension of A minus 1.
One, yes.
Yeah. So that's why, and you cannot say this, so that's why you are saying about co-dimension. So, proof. So let me discuss the proof. Yeah, so now, of course, yeah, so P contains I. Yeah, so you are interested in co-dimension. So you are interested about the length of the chain starting with 0, ending with P. So this implies that you can localize. Yeah, so actually you can localize by P. So, and we can consider AP. And this is actually the reason that why, so this shows actually the reason of the remark that we discussed before, that you can consider, so starting with prime ideal, yes, so you can consider either quotient or localization. Yeah, and in both rings you can take dimension. Yeah. So Krull dimension. So you can take dimension of AP, which is called the ordinary dimension. Yeah, and you can take dimension of AP that is called codimension. Yeah? And has geometric meaning of codimension. Why prime ideals are better, so you see this explanation, because if you have I arbitrary, you can take quotient,
Сейчас,
but you cannot take localization, so you do not have.
наверное, неразмерность API равна к размерности API.
Ну, нет, вот как раз тут надо взять размерность кольца, да.
Но это равняется к размерности чего-то другого исходного кольца. Ой, P просто.
P,
Да.
да, спасибо.
Four-dimensional P.
Codimensional.
Мгм.
I mean, by definition, this is codimension. And geometrically, this means that, so you have A mod I gives you the functions on the zero set of I, so you consider the flag on the subset, and this is precisely dimension of A mod I and the sequence between I and A of ideals because the flag just defined in this subset is just defined by ideals in between. And a codimension is just you're putting when you localize, so you're thinking about prime ideals that survive, and the ideals that survive and are still prime are prime ideals that are containing this ideal P. And of course, so this the sequence of the flag starting of your P is this has the dimension of the local ring, and this is codimension of varieties because you are taking the chain from your variety to the larger one. And so we can localize by now, and yeah, so of course, so since P is minimal, since P is minimal over I, minimal over I, this implies that A mod IP.
А это идеал, порожденный нашими
Да,
соотношениями.
это последовательность. But if you localize it, so this is an opinion local ring with ideal P, P modulo I. So this is the maximal ideal, and so you have to show so that for any Q, so we have to show that for any Q inside P in localization, codimension of Q is less or equal than R minus 1. Yeah, so then this will imply that this means the following. So this so if you have why it is sufficient, because if P has if we prove that P has codimension R, that means that you have sequence starting from P, etc., ending at P0, and of course for Q, this means that the length of the sequence is R plus 1, and this can be taken for Q, and since so we can take Q equal to P R minus 1, and this will give this will explain. So we can take for Q the ideal that is standing just right after P. Yes, so the largest ideal that is contained in P, and this will mean that if we had if we prove that for any such P the codimension is R minus 1, smaller than R minus 1, the codimension can be cannot be bigger. If you have larger chain of, then you take the last element in the chain and it has larger codimension. Yeah? So this means that it is sufficient to, so we can assume that Q and P has no ideals in between, no intermediate prime ideals. So this then we argue by induction R. Yeah, so R is the set of parameters on R. And just we shall see that codimension of Q is smaller or equal than R minus 1 by constructing sequence of elements in Q. Yeah, so with the condition it's not enough just to construct in order to prove this inequality. It's not just enough to construct the set of elements. Q should be minimal. So just in the formulation of that theorem, with condition that Q is minimal over I tilde. And this will be done via working with this regular with this sequence X. So proof of this construction of this sequence. Yeah, so Q. So we know that Q doesn't contain I, since Q is prime, and P is P that contains Q is minimal ideal over I. Yeah, so this means that some xi that some of the elements won't be Q. So and we can remember that. Yeah, so put x1 is not the element of the Q. So denote. Yeah, so обозначить. Denote it by x1. And this, yeah, so, but this means that, well, x1 is not in Q, and between Q and P there are no prime ideals, so this means that P is minimal ideal containing x1 and Q. I mean, this is just restated. So this implies that if you factorize by this ideal, then it just this implies that A mod Q x1 is Artinian local ring, as we have discussed. Local ring. Yeah, but you see that if you look at the sequence x2, the remaining part of the sequence xr, it sits in I and sits in P. Yeah, and so P is maximal ideal here. Yeah? The image of the only maximal ideal in P. So you have a sequence that sits in P. Q xi is Artinian. So this implies that maximal ideal is nilpotent. Yeah, so P in the image, so we'll let us put P of A into the P. P is a nilpotent ideal. Ideal in A QXI, X1. And in particular, all Xi's are nilpotent. And this implies that Xi's are nilpotent in AQXI's. So let us take this nilpotent degree. So Xi n is equal to 0 mod Q x1. And this you can write down Xi in the power n as I mean put the same n for put uniform n so not put but take. So take uniform n here for all i's. Take for any I. And you may write since we're taking this modular I, this means that we can write down it ai x1 plus yi. So for some elements for some yi that belongs to A. And of course yeah, so the not even so yi is they are not even the elements from A. By taking difference of right hand side, so these are elements of I. Yeah, so this means that yi also are the elements inside I. So this is subsequence in ideal I. And also yeah, so also we are taking, yeah, so notice that we are taking this decomposition, yeah, so just we are taking this by construction, xi to the power n is equal to 0 modulo this ideal. So this part it comes from x1 and this part comes from q. Yeah. So this means that we already constructed the sequence. So Q2, etc., YR, this is a sequence of elements in Q. So sequence in Q. And we have to prove, so we claim that Q is minimal. Claim that Q is minimal over I tilde. Yeah, so this is I tilde. So precisely you have actually maybe it would be good if I put here not x1 but xr, yeah, because for notation, yeah, but anyway. So you see that. But notice that between Q and x1 P there are no are the prime ideals. So you have xi to the power n, they belong to precisely the ideal generated by x1, y2, yr. And then for any p tilde that contain x1, y2, yr. Yeah. So if you take such ideal, so this would imply that p tilde will contain xi, xi to the power n, so xi will be contained in p, since p is prime. And this implies that, so all sequence is, so it generate I, so that means that this p tilde will contain I. So now let us, this is just a remark that if you have ideal already that contains this sequence, then it will contain I, and in particular, if you know that p tilde is some minimal ideal, and if it is inside P, it should coincide with P. So now let us put Q that contains y2, etc., yr. So now to understand that, we have to understand that Q doesn't contain small ideals. So let us recall that yi is equal to xi n minus ai x1, everything belongs to I. So let us, so here you take P, the projection to A mod I, and also we take P tilde, which will be projection to the quotient by this sequence, y2, yr. Yeah? So. And what we have to prove that Q will be minimal if Q is minimal if the ring will be Artinian. So now let us if this ring will be Artinian, and let us see. Is Artinian. And yeah, so let us yeah, so let us do it. Let us now study the. I mean, it will be Artinian if you localize by Q. But notice that so put P tilde to be the image of P. Yeah. Yeah, so P tilde, of course, will contain I modulo this sequence. And if you put pi of x1, it will belong to A, y2, etc., yr. Yeah. And notice that if you take P modulo, so P modulo this pi of x1, it is nilpotent ideal p tilde, yeah, so it is nilpotent ideal since first of all p contains I is minimal, so if you factorize p by I, this will be null radical of A mod I. And you have, there exists M, so such that P modulo I in the power M is equal to 0. Yeah, so this is the consequence of minimality. And so this implies, I mean, this kind of equality, so nilpotence of ideal implies that e to the power m sits inside I. Yeah, so this means that in the ring, this is just says that the image phi was the map from A into A modulo I. Yeah, so this says that pi of p in the power m is equal to 0. Yeah, and this can be reformulated that m spouts of p sits in I, but for any xi, the generator that belongs to I, you know that xi in the power n is written as ai x1 plus yi, and this implies that then it implies that for any x, if you raise x from I, yeah, if you raise it for so I is generated by this sequence xi. So this means that if generators are nilpotent, there exists n tilde, so which is actually n times r, the number of elements, so that if you raise x to the power n tilde, it will belong to ideal generated by x1 and yi. Yeah? And this это просто, ну как бы, если у нас есть это вот нейпотентность мини-радикала, да, если у вас есть образующая, то мы можем найти большую степень, ну, образующая как идеала, мы можем найти большую степень, чтобы n-та степень тоже. Ну, то есть n-та степени принадлежат идеалу, значит, можно возвести в большую степень, чтобы они принадлежали тоже. Любой элемент, который является линией, so any element that can be written as bi xi, if you raise it to this power and use binomial formula, that you will get that it belongs to this ideal. And this implies that if you raise p to some power m and then to m tilde, so this belongs to ideal x1, y2, etc., yr. And yeah, now we shall just okay. Я просто переверну страницу. Yeah, so now we have to do the following. So now we have to take pi of pi tilde modulo x1. It will be equal to pi. Извините, тут опечатка образ π. 3 π tilde. Π tilde это Давайте я напомню. P тильда это вот это отображение из А
По всему Y.
в Y, да, по всей Y. Вот. Соответственно, ну как бы вот это вот то же самое, что просто P тильда, но там значение у нас было x1. И это лежит, лежит внутри кольца А x1. Ну, я специально как бы пишу y2 и так далее, yr. Вот. И this ideal is not potent. Yes, so by the proof, so this ideal is not potent. Ну, то есть, потому что since the powers of P belongs to this ideal by which we factorize. Yeah? So this implies that the ring is Artinian, so this is only maximal ideal, since P tilde is only maximal ideal. So this implies that the ring itself is Artinian. And this implies that P tilde is minimal over x1 in the ring A to etc. YR. And now let us use we have proved there so that this ring is Artinian. Yes, so P is the only maximal ideal P modulo x1. So if you put it away, yes, so if you use only factorization by y2 yr, then P of course will be minimal over x1. If there are other ideals, other prime ideals, then you will get other ideals in so minimal prime ideal. Prime ideal. There could be many ideals, so minimal prime ideal. And this implies that so by Krug principal ideal theorem, principal ideal theorem, of course we have to use it somewhere. In this case, codimension of P tilde is less or equal than 1. So this means that between P tilde and 0 there is no more. So the sequences has the sequences of prime ideals can consist only of one ideal Q tilde. One prime ideal Q tilde. And this means that if you raise it to the power, so if you take the preimages, so you take the preimages of Q tilde, so this is also prime ideal, so this is P, and it contains the sequence y2, yr, and all intermediate. So if so all intermediate ideals between. So this implies that all intermediate ideals Q between P and y tilde just are of the form so you have to apply P tilde and the inverse to P tilde to Q and then to take P inverse of Q. Yeah, so they come from the intermediate ideal and the quotient. And this means that this map this map reserve taking pi and pi inverse. Q maps to pi tilde of Q in between. So it is Q tilde, and this is only prime ideal. So this implies that there are no more. I would like to say here I take Q. So if you take intermediate ideal Q, so they are on the form tilde. No, I just no. And the ideal Q in between P maps to the Q to the image, and if there are several ideals Q, then they will give several ideals in the image. So sequence Q1 and Q2 would give sequence in the image. And just if I put Q as here. So this tells you that, and since in the image you have only one ideal in between, so this is contradiction. So this implies that Q is only ideal. Q is only ideal in between. Of P and y2, y1. So you do not have small ideal, so by induction, codimension of Q, dimension of Q is less or equal than R minus 1 because there are R minus 1 elements. There's no so the idea is to put by this constructions to put the idea. Все, мы
Да, Максим просил сохранить в формате PDF
Да.
конспект.